Welcome to the solutions to the Regents Physics Waves and Sound problem set. Problems number 6 through 8. Let's get started with number 6. An ocean wave has a length of 10 meters, so that would be its wavelength, and we give that the symbol lambda. A wave passes a fixed location every 2 seconds. Well, one wave every 2 seconds would be the wave's period, so we underline that and give that a capital T. What is the speed, that is v, of the wave? All right, we start out with the wave equation, v equals f lambda. We're looking for v, we have lambda, but we don't know the frequency. However, we do know the period, and we know that the frequency is the inverse of the period. So since f equals 1 over t, we can substitute 1 over t in place of f, and that makes our equation lambda over t, or lambda times 1 over t, which is the same thing. We go ahead and we substitute our values. The wavelength is 10 meters. Our period is 2 seconds. And of course, 10 divided by 2 is 5, with our units being meters per second. On to number 7. Water waves in a shallow dish are 6 times 10 to the negative 2 meters long. That would be 6 centimeters. At one point, the water oscillates up and down at a rate of 4.8 oscillations per second. So the 6 times 10 to the negative 2 meters long is going to be our wavelength. And then the 4.8 oscillations per second is disguised as frequency. Typically, the units of frequency is hertz, but other units you will see are oscillations per second, waves per second, vibrations per second. If you see any of that, you should recognize it as frequency. So our frequency is 4.8 hertz. All right, A, what's the speed of the water wave? We're looking for V. So naturally that would be V equals F lambda, our frequency 4.8 hertz, times our wavelength 6.0 times 10 to the negative 2 meters, gives us a velocity of 0.29 meters per second. B wants to know the period of the waves. Well, that's related to the frequency because it's the inverse of the frequency. So we go ahead and substitute there, and we get T equals 1 over F equals 1 over 4.8 hertz. We take the inverse of 4.8, and we should get 0.21 seconds to 2 digits. Lastly, number 8. Water waves in a lake travel 4.4 meters in 1.8 seconds. This problem's a little tricky because it's actually giving us the distance the water waves travel, and the 4.4 meters is not the wavelength of the waves. It's the distance the waves are traveling. And it gives us the time in which the waves are covering that 4.4 meters. They also give us the period of oscillation is 1.2 seconds. So we underline that and label it with a capital T. What's the speed? Well, you would just use traditional velocity equals distance divided by time to calculate part A. 4.4 meters covered in 1.8 seconds. 4.4 divided by 1.8 equals 2.4 meters per second to 2 digits. What is their wavelength? Well, same as what we covered earlier here. We know the speed is 2.4 that we just calculated in part A. They want to know the wavelength. What are we missing? Well, V equals F lambda. You could use that equation we derived earlier in number 6, or you can just go ahead and find the frequency first and then substitute it. That's what's been done here to show you an alternate solution. So we know the period is 1.2 seconds. So F equals 1 over T. 1 over 1.2 seconds gives us a frequency of 0.8 hertz. We now go ahead and substitute that in to our equation, and we have 2.4 equals 0.80 hertz times lambda. Taking 2.4 and dividing by 0.8 gives us a wavelength of 3.0 meters. All right, that'll do it on the solutions for numbers 6 through 8. More to come as we do numbers 9 and 10 together in class tomorrow.